Hello everyone. In the past few sessions, we have been dealing with tensors a lot. We have looked at what tensors are. We also have understood the different type of operations that we can perform using tensors. In one of our previous sessions, we also have dealt with the difference between using tensors versus NumPy arrays. So tensors has this ability of auto differentiation, that is computing the gradients in backpropagation process, whereas NumPy arrays do not have. And we also can push our tensors onto GPUs and perform our operations on GPUs rather than on CPUs. So these are two primary distinctions of using tensors over NumPy arrays, typically when we are trying to create deep learning models using PyTorch. So now in this submodule, we are essentially going to look at creating linear regression model using PyTorch from scratch, that is by using PyTorch tensors alone. And later we'll implement both gradient descent as well as linear regression using built-in modules of PyTorch. We'll understand the difference between these two cases that we are going to implement. Clearly, we will get to know the level of complexity that is reduced by using the built-in modules over this existing set of statements or sequence of steps that we are going to follow while creating this linear regression model just by using tensors alone. Okay. So in this session, the next session, we are greatly going to understand the different steps that are involved in the process. Also going to understand the gradient descent algorithm on a whole. Most of you might be already familiar with the gradient descent algorithm, but I'm going to revise all the concepts related to it in this and the following sessions as well. Okay. For this particular exercise, we are going to make use of housing price dataset. So I have just sampled certain features alone and certain observations alone. I just do not want to consider the complete dataset and overwhelm you with writing too many lines of code. But at the end of this particular submodule, we'll be solving a particular real world problem. Let's not worry about that. So here we have considered three different variables: crime rate, the average number of rooms in the neighborhood region, and age of the building. So each and every observation that's present within this particular structure data would denote a house. So this is house 1, 2, 3, and so on till n. So there could be n possible observations with three different features here. The first feature is crime rate within the neighborhood region. RM is going to be average number of rooms in the neighborhood. Age is going to be age of the building. So we have one y variable. The y variable here is going to be the median value of the house in thousands of dollars. So when I say 29, it's going to be $29,000. Okay, so that's how you need to interpret the target here. We are essentially going to create a linear regression model, which is nothing but the weighted sum of different inputs that we are having and the intercept as well. So we are now considering this particular neuron, and there are three different inputs that this particular neuron would receive. Is x1, x2, and x3. x1 here is nothing but the crime rate. x2 here is going to be RM. x3 here is going to be age. Every single input that this particular neuron would receive from the preceding layer has got a weight associated with it. I'm calling it as W1, W2, and W3. There is a bias term that's also associated with this particular neuron. And we are essentially going to consider Z here. Z is nothing but the weighted sum of all of these inputs. The weighted sum of all of these inputs. And then we are adding this bias term as well. If you closely observe, these weights are nothing but the coefficients that we have already learned during our machine learning series. And B here is nothing but the intercept. So we have represented a linear equation as beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 and so on till beta n xn. So beta naught is being replaced with B, which is bias. Beta 1, beta 2, beta 3 and so on are now replaced with these weights, which are nothing but W1, W2 and so on till W3. So the activation function here is a linear activation function. I'm not going to change any of the output that's computed here. So this here is a continuous value. So the output here is a continuous value. So we clearly understood the architecture now. So with this architecture as background, let's proceed with this particular coding exercise. So all that we are trying to compute here is consider certain random values for weight vector. So this is my weight vector. My weight vector here is going to be W1, W2 and W3. So there are three weights that I'm considering. Only one bias that I'm considering, which is B. So I'm initializing this weight vector and bias with some random values. So there are different weight initialization techniques which we'll cover later. But for now, let's understand that we can consider some random weights associated and random bias associated with this particular model that we are creating. Okay. So X and Y data, I've just considered some random observations. So I only have 6 different observations that are considered now. And this is my Y data. So my Y data here is going to be the median value of house, which is expressed in terms of thousands of dollars. So when I say 24, it's going to be 24K dollars. When I say 7, it's going to be $7,000 and so on. So now we need to model this input data. We are going to consider these actual Y values while creating the model. So now I have created 2 different NumPy arrays. So let me run this particular code, which will import all the necessary libraries for us. So I have imported NumPy, pandas, just turned off the warnings as well. Now clearly we have created 2 different NumPy arrays, X and Y. I'm going to create tensors out of it. For that, I'm going to make use of this function called from NumPy. Within the parentheses, I'm providing X. So similarly, I also would want to convert this Y NumPy array into Y tensor here. So X and Y data is going to be pretty much the same, except that the type of these objects are now tensors and no longer arrays. You see the type of it. The type of it is going to be array earlier, and now it's tensor. Okay. So once we have created the input data as well as target, so this here is input data, this here is target. So once we have the data ready, we are now going to create a function which we are calling it as model. So model considers X data. And before we create this function, let's initialize random values. Initialize W and B vectors, right? So initialize some random values. I would essentially consider this random function, which is going to generate some random values, which follows a standard normal distribution, which draws a particular value from a standard normal distribution. So I need 3 different weights. So the weight vector is going to be 1 by 3 in shape, because I only want one single row, because I'm expressing it as a vector, not as a matrix, right? I also would set this particular parameter called requires grad to true, because I need to compute the gradients in my back propagation process. So this here is my W vector, and the second statement is for my B vector. So I only have one particular bias associated. Now you look at the W and B that's being initialized here. So these are the different values for weights and biases. So if I'm running it again, I generate completely different set of values here. Since we are randomly drawing this particular values for weights and biases from a standard normal distribution. So that's the functionality of random function here. Nothing apart from that. So now let's create this model function. The model function is going to be what? The cumulative sum of weighted inputs. That's all. So the cumulative sum of weighted inputs as in X multiplied by W transpose plus B. So here at the rate is nothing but the matrix multiplication that we are doing in between W transpose and X. I'm representing it as W transpose X plus B. That's all. So this here is my predicted output. I'm representing this as spreads here. I return this spreads from this particular function. So whenever I'm invoking this function with X data, we are now getting the values stored in predictions. You can inspect what predictions are and what actual Y's are. You clearly understand that there is a huge deviation in between the predicted output as well as the actual Y values. So the loss when you compute is going to be very high, because your predicted values are way far apart from your actual Y values, for the reasons that we are completely aware of, because we have randomly initialized our weights and biases. We do not know what could be the optimal weight and bias here. So gradient descent algorithm is all about understanding what are the right values for your model parameters, W and B. What are the right values for your model parameters, weights and biases is what forms the optimization process here. Gradient descent algorithm is all about that, is all about finding the right values for your W and B. So now let us consider creating the loss. So for that, I am going to define or write a new function. I'll write new function here itself. So define MSE. MSE is mean squared error. So I'm considering MSE as a loss function for my model, because I need to understand how different my predicted Y values are when compared to actual Y values. Predicted and actual Y values are the input parameters that I can define for my new function called MSE. We clearly take the difference between Y and preds, Y and Y preds, take a square of it, and then consider taking a mean of it. That's nothing but the function of mean squared error. I'm returning this value as loss. So now I can calculate the loss by just invoking the MSE, providing y and y parets as arguments for this particular function. Let's also inspect what could be the loss here. Loss will be very huge. 6761 is a very high loss for the initial model that we have created. So now let's implement the gradient descent process here. So with torch.noGrad, I'm just informing PyTorch not to compute any gradients now. Okay. So what am I supposed to do? In the gradient descent process, if you consider this as your loss function, my loss function clearly is mean squared error, right? So this is my loss function. And this here is going to be, on y-axis, it's going to be MSE, loss function which is expressed in terms of yi and yi hat. And on x-axis, it's going to be w. If at all we are considering weight is the only parameter. So this here is a three-dimensional case. So we are having weights and biases both. And there is a weight vector as a whole. But for simplicity, if we are considering that there is only one particular parameter that we are planning to optimize for, this is how the diagram would look like. So I would come up with an initial random value for my weight, right? This is my random initial value. When I draw a tangential line, I just check the slope of it. The slope of it is positive, but I clearly know that this is my minima point. Whatever w that I find at this particular minima point, at the minimum loss, is my right w value that I need to find so that the regression line that I come up with is more appropriate, which is producing a minimal loss possible. So we clearly know that the slope is positive here. Since the slope is positive, we need to subtract some value from your existing w. From your existing w, you need to subtract some value. What is that value? That value here is going to be dl by dw. This is nothing but a gradient. But I do not want to subtract whole of the gradient, but a small proportion of gradient which is defined by eta. So eta here is going to be learning rate. So learning rate is a model hyperparameter. So this here is a hyperparameter. And w here is going to be model parameter. Model parameter is what you need to find during the gradient descent process. So hyperparameters are defined before you create the model itself. For now, I am going to consider a value of 0.0001 as a learning rate. I'm just going to take some small value of what my gradient is to be subtracted from my actual w value in order to attain my next w value. So w next here is going to be this value now. I took a small jump in the direction of minima here. So this is my next w. And I again compute the gradient at this particular step. I again understand that the slope is positive. I take another jump, I update the weight again. In the subsequent iteration, I update my weight again. And I continue this process till I observe this minimum point, till I observe convergence. So whenever you draw a tangential line at this particular minima point, we clearly know that the slope or gradient of loss with respect to w is 0. Or if you're not observing any change in the previously updated weight or in the current updated weight, then you stop the gradient descent process, stop the iterations there. And that's called the convergence point. So in essence, this is a gradient descent algorithm. So you need to implement this now. What are we supposed to do? We take this particular formula. So we currently have weights and biases already defined, the random initialized weights and biases. I'm going to subtract this particular value. And we know that back propagation, so loss dot backward, which is a back propagation. So here, this is a forward propagation that we have done. When I invoke this function, it's nothing but forward prop. In forward propagation, you are taking the weighted sum of different inputs, adding the bias term. In the backward propagation here, loss dot backward, you are essentially computing the gradients. Now, if you look at invoking this attribute w dot grad, so w is a weight vector, right? So w dot grad now stores all the gradients. So b dot grad also has got the associated gradient with the bias term. Since we already have the derivatives, we can simply implement that function. So the updated w is going to be w minus, so I can rewrite this as, w minus eta times lr times w dot grad. So instead of writing this equation like this, I'm just writing w minus equal to, which is nothing but the same. So lr here is going to be eta. Eta value, I'm initializing it as 0.0001. Similarly, I also recompute or update my bias term here as b.grad, LR times b.grad. So once we update weights and biases, we are now going to actually initialize the gradient to 0, because we are informing PyTorch not to take the cumulative sum of gradients that are computed in iterations that are conducted as part of gradient descent algorithm. Okay. So w.grad.0 is going to reinitialize the existing gradients of these weights and biases to 0. This is an important step to note. So once this process is done, so once the weights and biases are updated, you consider looking at the weights and biases. So the weights and biases are now updated. So they clearly are not the same as what you have observed earlier, right? If you look at it, they are nowhere close to what you have observed earlier. Like 0.1170 was the initial weight. Now 0.1195 was the updated weight. And the third weight within the weight vector was minus 1.01. Now this here is going to be 0.21. Now you can simply go about generating the predictions again, the second iteration. So this here is the second iteration that I'm conducting now. We also look at what the loss is by invoking MSE function, by providing actual and predicted values, call it as loss, and look at the loss value now. The loss value is 304, which is way lesser than the initial loss value of 6761 that we have observed. But this has to be an iterative process. We cannot only conduct 2 iterations. Right? So now I'm going to rewrite the code. I'm going to rewrite the complete code. So now we have one forward pass. So in order to do backward pass, we need to compute the loss first. And then loss dot backward is going to help us do the backward pass where the gradients are computed, where the gradients of weights and biases are computed. So now I have conducted forward pass, computed the loss, and then backward propagation where the gradients are computed. Now we need to adjust the weights. I'll just cut this whole code, paste it here, just move this LR step above, and then we are re-updating the weights and biases in this particular step. And once this whole statements are written, I am going to iterate this over a number of epochs. For epoch in range of 100, I am undergoing 100 different iterations now. In each iteration, there is a forward pass and a backward pass. And for every iteration, or for every epoch that's conducted, to be more precise, for every epoch, we are updating the weights by using the gradients that are computed during the backpropagation. Okay. So let me rerun this whole code. I've rerun this whole code, but for simplicity, it's better that we actually rerun right from the beginning. So the weights are reinitialized, and the weights are reinitialized now with different values. We actually rerun the functions that we already have written. And now this is the whole code that we have written based on the steps that we have followed earlier. And now let's recompute the loss. Let's look at what loss is. Let's look at what loss is now. Loss here is going to be like 237, which is way lesser than 6761 that we have looked at initially. Now we can also investigate what final predictions are and what my actual values are. So let me delete all these steps, the below steps. So the final predictions are this, and the actual Y values are these. So we clearly note that there's no good variance among the Y parades. And here there's a fourth observation which has got $50,000, which is like $21,000 is what we have predicted. There's a huge deviation there. So 237 MSE is not good at all. Is not at all good. So we need to further improve our model. In order to improve our model further, I would like to increase the number of epochs from 100 to 1000 this time. So let me rerun this whole code. Let me actually reload the NumPy arrays, the torch tensors, and then reinitialize the weights. Let's rerun this whole iterative process. Now let's look at the loss. The loss is greatly reduced to 45. The predictions now and the actual Y values are pretty close to each other. Now it's 41.13, which is close enough to 50. And this here is 16, which again is close enough, pretty close enough to 7, but it's not that close yet. But however, the other values, like if you see the third observation, it's 32, which is very close enough to 39, the actual value of 39. So 34 also is close enough to 33. We further can improve this particular loss that we are observing, but for now, we are leaving it here since we have attained a decent enough MSE value and our predictions are pretty close to the actual Y values when compared to our previous results that we have observed so far. Since this is a plain and simple architecture, like we only have one neuron, 3 different inputs, one output. We have not followed any weight initialization method here. So there were very large number of weight initialization techniques like Xavier Glorot, K initialization and all, which we have dealt with in our previous module. We'll also cover again. But however, we have not incorporated any of those techniques. We randomly have selected some weights and biases and inputted that with only one single neuron in the whole neural network architecture here. So if we further expand this to multiple hidden layers, or sorry, expand this to having multiple hidden layers or multiple neurons within specific hidden layers, then there is a quite a bit of chance that your model is going to perform way better than what it is now, since you are introducing complex features here. As we have learned earlier, as we increase the number of hidden layers, the level of abstraction increases, the level of complex features that are derived from the existing data is also increased. So you predict or you generate the predictions way better than what you have generated with a simple naive architecture. What we have considered is a simple and naive architecture for now. Okay. In the next session, we are going to discuss more on what gradient descent algorithm is all about. I know that you have got a fair understanding of what gradient descent is since we already have implemented it now. But for the sake of better understanding and not letting any of the gaps pitch in, let me cover the gradient descent algorithm in its entirety in the next session. Okay. So that's pretty much all I wanted to discuss with you in this session. Thanks for watching.